remind you, I think I said it before, but in case not all of you were here, and also for the purpose of people who aren't here, now that I'm recording, the way I do that, okay, on YouTube, the recordings are in what they call the playlist, okay? And how I do that, I don't wipe out the playlist and start again every term. I leave everything in there from the previous term, just for the reason, in case something happened like happened yesterday, Tuesday, that the system went down, okay? And I couldn't record Tuesday, so, and if you've noticed, if you've been on the playlist, this term stuff is all at the bottom of the playlist. The last terms is at the top of the playlist, okay? So I hope you've been going down to the bottom to see the stuff if you are watching it. So what I'm going to do now, when I record and get this one gets uploaded to YouTube and everything, which will probably be late this afternoon before I'll be able to do this, because all my classes go right after another today. But late this afternoon, when I do get them uploaded to YouTube, what I'll do is I'll look at the last one that got recorded, the one from last Thursday, and then I'll look at today's, and anything that's missing in between. And what I've been doing in the past, once I record a thing, then if I see it's from the previous time I already recorded, then I delete them then, okay? So this time I won't delete those at the top, or near the top, somewhere up there, that fill the gap between last Thursday and this Thursday. So for the ones we missed, and it's not going to be an exact fit, because last time I taught this course, I think it was a regular term, which is hour 15 minutes each. This is hour 50, so obviously they can't possibly fit together. But I'll try to leave one or two lessons out there from somewhere near the top. Now, there's some other things in this class that probably are at, I don't know, that may have been the other class. I think that was differential equation. So these should be near the top. And so I'll leave those and keep those in place, and then from then on, only replace the ones that look like they're duplicated. So there'll be one or two that probably are not. And there may be some overlap and some gaps, but I'll try to minimize that as much as possible. Any other questions or any questions? All right. Now, my mark here, unfortunately, I have 3 marks on this one page. I didn't do a good job of erasing. In fact, I didn't erase at all. Someone remind me, oh, we were just going to start the transpose of a matrix, right? That's where we ended last time, right? We did number of solutions. Yeah, I remember doing that. So we're at the top of page 57. Chapter 2, Matrices, 2.2, Properties of Matrix Operations, and we're going to cover a new property, and this is called the transpose of a matrix. Now, they have a little discovery here. Sometimes these are helpful, sometimes they're almost just a pain. But let's see what this one says. Here's an A. This is before the transpose. Let me get my pen set up. It's not setting up. There we go. This is discovery on the left inside margin. Okay? Let A be this matrix. 1, 2, 3, 4. Pretty creative matrix. Okay? And let's let B equal this matrix. 3, 5, 1, negative 1. Okay? Oh, sorry about this. It does require the transpose. Why do they put it before we talk about it? We may or may not come back to that. Let's delete it for now. We'll come back if we need to. Let's first talk about what we mean by transpose of a matrix. Not all of you have books, so let me write this down. The transpose of a matrix, okay, is formed by writing the original matrix columns as the rows in the new matrix. formed by writing, the way they say it, the columns as rows, okay? It sort of leaves a little bit out, but that's exactly what happens, okay? You exchange the rows and columns. So here, A is an M by N matrix. I love writing these. They're so much fun. A11, A12, A13, dot, 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 up to, and it's a M by N matrix. So how far would this go? A sub would be the subscripts. What would be the subscripts? That last entry in the first row. 1N, perfect. And how would the next one begin? Help me. 2-1, A 2-2, A 2-3, dot, 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 up to A 2N, perfect. A 3-1, A 3-2, A 3-3, dot, 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 to A 3N. We'll dot, dot, dot on down. What would be the last row? What would that be? A second? M1, A M2, A M3, so M, dot, 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 everywhere, dot, dot, okay. What would the last one be? MN. Okay, there's your original matrix A. Now, the transpose of A, and we call this A superscript T. Okay? Now, earlier we're using superscripts to be powers, you might say. You know, when you're multiplying A by itself, by itself, by itself, of course those A's all have to be square matrices, then that can be A to the 7th or however many times you multiply it by itself. That's one superscript, if it's a number. If it's a letter, T, capital T, that means the transpose. Now, does anyone want to initiate what you think the first entry would be? 1-1. Very good guess, okay? Now, the key comes in the next one. What would that be? 2-1. Notice what was in the column, first column of A, is now going to be in the row here. So this will be A 3-1, dot, 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 up to A M1. And next row would start with A 1-2, A 2-2, A 3-2, dot, 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 all the way up to A M2. And then a A1-3. Notice what were the rows are now the columns. A 2-3, let's see, 2-3, A 3-3, dot, 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 up to A M3, and then another bunch of dot, dots. Okay, and what would be the last one? Last row? 1N, A 2N, A 3N, and then dot, 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 and dot, 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 everywhere, dot, dot, to A MN. So there's a problem here, folks. Yeah? Okay. Yeah, that's correct. Those are the entries. But notice the size of this matrix. What is its size? N rows by M columns. Okay? So I use the same subscripts here, but they're out of place there, okay, obviously. But this corresponds to that one because they're the same values, but now that's in the M corresponds to a column rather than a row. So that's why I suddenly say, wait, I got the subscript wrong, but no, we intentionally reversed the subscripts there. So that's in by M. So, one thing to note, maybe several things to note, but when you have A superscript 3, that's got to be a square matrix, remember? You can't multiply a matrix by itself over and over again unless they're all the same size, okay? But A sub t, when the superscript is that letter T, yeah, no reason for these to be the same. M and N don't have to be the same. These don't have to be square matrices. But if A is a rectangular matrix, A sub t is a rectangular matrix also, but in the different long dimensions. Okay. I don't know if that makes sense or not. Okay. Let's go back and perhaps do our discovery. See if we discover anything. A was, this is what I started to do before, 1, 2, 3, 4. And B was 3, 5, 1, negative 1. Okay? It says calculate first the AB transpose. So the first thing we do is AB. What is AB? Can you even do that? Yes, and what size will it be? 2 by 2. Help me fill in the gaps. The 1-1 entry would be 5. 1-2 entry would be 3. 2-1 entry would be 13. Is that what you said? Okay. And here's Travis. Perfect attendance today. Way to go. Ding, 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 ding. Okay. Cha-ching or whatever. Okay. And we're doing example 8 on page 57 in section 2.2, chapter 2. Okay, and we just had one more to do. We're doing the product of that A times B. What is the 2-2 entry? 11. Okay. Now, they didn't really ask for that. They asked for AB transpose. So what is AB transpose? This is a new concept today so far. What would that be? Say 5 will stay 5. And what? 13. It goes here. 3, 11. Okay. So, all right. Now, another thing they wanted us to do was multiply A transpose by B transpose. So what in the world is A transpose? You tell me. Help me. Second. 1, 3, 2, 4. And what is B transpose? We're exchanging rows and columns. That's what a transpose is. Say again. 3, 1, 5, negative 1. Okay? So now let's do A transpose, B transpose. Can you do that? Sure. What size? 2 by 2. So what's the 1-1 entry of that one? 18.
1, 2 entry. -2. 2, 1 entry. 22, 26, right? Okay, 26. Okay, and the 2, 2 entry. -2. All right. Doesn't resemble anything we've had before, right? Okay, but let's do something else. Let's do B transpose A transpose, where A transpose is 1, 3, 2, 4. I sort of like to write them again on the right side so you don't get as confused. So let's do B transpose times A transpose. Number 1, can you even do that? Sure. What size does it come out to be? 2 by 2, just like before. Every time before, because they're all square 2 by 2 matrices. So I wrote them down here so you can get them in the right order. What's your 1, 1 entry? Anyone do it? B transpose A transpose. Second? Help me, somebody. One entry. B transpose A transpose. 5. 1, 2 entry. 9 plus 4 is 13. 2, 1 entry. 3. And 2, 2 entry. 15 minus, 15 minus 4 is 11. Okay. Now, what do you notice? AB is the same as B transpose A transpose. Okay? Kind of interesting, huh? Now, this doesn't prove it, but we've seen other combinations, they're nowhere close. No, I'm sorry, I said it wrong. AB transpose is A transpose B transpose. Okay? Yeah, that makes more sense. I thought that shouldn't need to be the case, but it's not. This is equal to that. So those two are indeed equal. That when you do the transpose of a product, it's the product of their transposes, but in reverse order. Okay? Not just the product of their transposes, but the reverse order of the product of the transposes. So, that was just the discovery. I think we'll get to that a little bit later. They like to introduce you to stuff first, have you think about it, and then later give you the rule. So we're going. Goodness gracious. It's about this time of morning, every morning, suddenly my eyes get totally dry. Now I think part of it, and now that I think about it, it's true. My computer here has a fan, and there's a lot of hot air being blown out of it. And when I sit here too long, that's blowing right into my eyes. I think that must be it. It just dawned on me. That's what I'm doing. I need to get up and talk more there, but in this class I'm writing almost the whole time. So here's matrix A. Pretty complicated matrix. 2, 8. What would be A transpose? Okay, but tell me how to write that. All in one row. 2, 8. Okay? Because if A, what size is A? So A transpose must be a 1 by 2. Yeah, you got it. Okay? That was fairly easy. Let's do B. B happens to be 1, 2, 3, 4, 5, 6, 7, 8, 9. Really creative matrix here. what would be B transpose? One, 4, 7, 2, 5, 8, 3, 6, 9. Okay, very good. Let's do C. 1, 2, 0, 2, 1, 0, and 0, 0, 1. What would be C transpose? One, 2, 0. I thought you just said that. Next. 2, 1, 0. Huh? 0, 0, 1. That's rather bizarre, isn't it? Okay.
This matrix is its own transpose. Most of the time that will not be the case. In order for it to be the case, number one, you must have a square matrix. Okay, it could possibly be if it wasn't square. But not all square matrices will be their own transforms. The other thing to note here, now in this case, your main diagonal were all ones. That's not required, okay? But in this case it is. Doesn't matter what the main diagonal is, but what has to be the case for it to be its own transpose is that the opposite elements are identical across that main diagonal. And what we call that is a symmetric matrix. Okay? Because across the main diagonal you have exactly the same matrix. Okay, does that make sense?
All right. Now that's jumping ahead a little bit. Oh, no, it isn't. It's your marginal comment there. On number C, note that the square matrix in part C is equal to its transpose. Such a matrix is called symmetric. A matrix A is symmetric when A is equal to A transpose. That's a definition that you'll probably need in the future. Hint, hint. From that definition, it should be clear that a symmetric matrix must be square. I said that already. And also, if A is equal to what they're saying here is if A is defined to be all these individual entries, Ij, where I is going from 1 to M, but J is also going from 1 to M, remember they have to be square, then the Aij is always equal to Aji for all I not equal to J. Okay? Of course, if it's equal to J, then you're on the diagonal. So you have to be equal to yourself. Let's do the one more here, and that's this matrix D. And this matrix D is 0, 1, 2, 4, 1, negative 1. And what would be its transpose, D transpose? 0, 2, 1, 1, 4, negative 1. Perfect. Okay. So, that being said, sorry. I think along with the eyes drying out, my whole head is drying out and having trouble breathing, having trouble thinking. Okay. Let's clear the ink. And because some of you don't have your books, let me write this down. Theorem 2.6, the properties of transposes. If A and B are matrices,
Okay, that's what they usually are. With sizes that the given matrix operations are defined. I'm just going to say with appropriate sizes. Some things would need to be different sizes from others. C is a scalar. Then the following are true. Okay. 1. Hopefully this makes sense. What if you took the matrix A, transposed it, and then took that matrix and transposed it again? What are you going to wind up with? Second? You get the original A. Absolutely. Because what you've done is taken the A, exchanged columns and rows, and then exchanged columns and rows back. So now what was originally a row is back being a row. One transpose makes it a column, the second one makes it back into a row. So yeah, you get the same matrix. So there's the first, and pretty obviously, that's the transpose of a transpose is the original matrix. Number 2, what if you have the sum of two matrices and you transpose the result? What does that give you? The transpose of A plus the transpose of B. Now, you can either keep the order or change the order. It doesn't matter because when you add you're just adding the elements. Okay. Now, this one could be any size matrix. A, any size. And the transpose of the transpose back to the original. Here, what has to be true about A and B? They have to be the same size. They don't have to be square, just the same size. But then, of course, the transposes will be not the same size as A and B, but they will be the same size as each other because you've just exchanged rows and columns. Okay? So the size makes sense, but the order doesn't really matter. Now, here's number 3. Okay? Now, this only works with scalars. C, A, that is a matrix. A is a matrix, C is a scalar. CA is a matrix with every element in A multiplied by the common C. And if you take that and transpose it, okay, that's exactly the same thing as C times A transpose. All right. Okay. C times A transpose. Now, number 4 is the one we noted in the discovery. What do you reckon AB transpose is? Any ideas? We just did it in the discovery. We showed it for a 2x2. It's what? B transpose times A transpose. Exactly. The transpose of a product is the product of the transposes, but in reverse order. Okay. Now, here, when we did it in the discovery, we used the square matrix, which the size didn't help us in. But what sizes must A and B be? Must they be the same sizes? That's just
You make up a name for the size of A. Letter by letter. M by N. So what size must B? N by, let's say, P. Doesn't have to be the same. Now, the transpose, okay, the product of those would be what? M by P. And its transpose would be P by M. Okay? Now, if you tried to do an A transpose B transpose, if you tried to do that, that would be, if you did the A transpose B transpose, that would be an M by N by M by P by N. Guess what? You can't even multiply those at all. So therefore, you've got to, and what happens here? What would the size of B transpose be? What's the size of B transpose? P by N. And what's the size of A transpose? N by M. And guess what? You can multiply those, or you couldn't do it if you had put them in the same order they were. And what size do you get? P by M, which is the same size as this. Now that doesn't show they're the same. It means they're the same size, but what we showed before and what they're telling us here, not only are the sizes the same, the matrices are the same. Okay? So you see you've got to change the order of B and A. Okay. The transpose of a product. Now, there you go about proving property 1, which is pretty simple to prove. It makes sense logically, so I'm not going to take lots of time. But if you're interested in doing proofs, not a bad idea to look and see how they go about saying that here. They generally use the IJ way of expressing the matrices, and that's the way to go. Now, properties 2 and 4, they say, can be generalized to cover any number of finite number of matrices. In fact, number 2, if you had more than one, like A plus B plus C, how many do you want? Is that enough, or you want more? That's enough, okay? That sum transposed, guess what it would be? A transpose plus B transpose plus C transpose. So it just doesn't work for 2, it works for as many as you'd like to have. How about this one? A times B times C, how many more you want? Any more? That's enough, okay? That transpose, guess what that answer is going to be? Anybody? C transpose times B transpose times A transpose. Okay. Now, of course, the sizes have to make sense. You have to go through and do this. This was a M by N, and this is a N by P, and this is a P by Q. And the product of all those are M by Q, and then the transpose is Q by M, and then if you started that over again here, that will work. Only if you reverse the orders. Okay. So those can be generalized. Any questions? Let's go to example 9. Here is matrix A. 2, 1, negative 2. Negative 1, 0, 3. And 0, negative 2, 1. Okay, here's matrix B. 3, 1. 2, negative 1. And 3, 0. Okay. I wrote those awfully close together, didn't I? Now, the first thing it says do is AB. Can you do AB? Okay. What size will it be? Second? 3 by 2, exactly. So it'll be 3 rows, 2 columns. Okay, you tell me what the first entry will be, the 1, 1 entry. 2, very good. 1, 2 entry. 1. 2, 1 entry. 2. Okay. I just got lost myself. Okay. I wrote those too close together and I'm having trouble seeing. 1, 2. Yeah. 6, you said? Yeah. Next. Negative 1. Perfect. Next. Say again. Negative 1. Okay, I thought you said negative 5. Okay. Negative 1. Okay. And last entry. 2. All right. Next thing it asks us to do is transpose that. So what's A, B, transpose? What size will this be? Okay, it'll be a 3 by 2. I'll do this. What will be the entries? 2, is that what I heard? 6. Negative 1. 1. Negative 1. 2. Goodness, I can't write. So negative 1, 2. Okay. All right. Next thing we wanted to do is do B transpose. What size will that be? B transpose. B transpose. 2 by 3. And what will its entries be? All right. And how about A transpose? What size will it be? 3 by 3. Okay. And what will it? Say again? Is that what you said? Oh, I'm sorry. I can't hear, so I thought you said it right. Okay. So what would that be? 2. Negative 1. 0. Right. Yep. Yep. Negative 2. 3. 1. Blast off. Okay. Now, the last thing it wanted us to do was do B transpose A transpose. Can we do that?
What size is B transpose? 2 by 3. And what size is A transpose? 3 by 3. Can you multiply them? And what size will your result be? Say again? 2 by 3, is that what I heard? Okay, I can't hear, so I'm hoping that's what I heard. Okay, so let's do those. The 1-1 entry, B transpose, A transpose, would be what? 2. 1-2 entry would be 6. And 1-3 entry would be second -1. Is that what I heard? My hearing's bad. Okay, -1. Okay. All right. Yeah. Yeah. All right. 2-1 entry. One. 2-2 entry. -1. And 2-3 entry. 2. Okay, and what do we notice here? The AB transpose is exactly the same as B transpose A transpose, which is in accordance with your fourth rule property from the previous page. Okay? Now, one other thing before we move on, and I'm so sorry, my eyes are so dry I can't get any moisture in them. Okay. What is the product of a matrix and its transpose? So the matrix here is A, and that's going to be 1, 3, 0, -2, -2, -1. And what would be its transpose? You tell me. 1, 0, -2 is the top row. 3, -2, -1. Goodness, my eyes hurt. Is the second row. Okay? Now, for any size A, M by N, you can always multiply it by its transpose, which is an N by M, right? Because when you transpose it, the number of rows of the second one becomes the number of columns of the first, because that's what you're doing. You're exchanging rows and columns. So you can do that. What will be the size of the product? This product. Say again? 3 by 3. Now, if you keep it generic, M by N by N by M, you're always going to get an M by M, which means it's a square matrix. Now, if it had been reversed, it would still be a square matrix, like A transpose times A. Okay? it would be a square matrix, but guess what? Different size square in this case. That would have been a 2 by 2. Because then you would have had a 2 by 3 by 3 by 2 would be a 2 by 2. This is a 3 by 3. So whenever you multiply a matrix by its transpose, you'll get a square matrix, but changing the order of the multiplication will still result in a square matrix, but it may be a different size. So, that being said, let's do the multiplication. 1 entry would be 1 entry would be, second, 10. 1 2 entry would be -6. 1 3 entry would be second. I can't hear. -5. Perfect. Okay. 2 1 entry. I can't stand that. Okay. 2 1 entry. -6. 2 2 entry. 4. 2 3 entry. 2. 3 1 entry. Okay, I just lost where I was. 3 1, yeah, would be -5. Okay, next. 2, next. 5. Okay. Can you tell me something about that matrix? It's symmetric, exactly. It doesn't matter what's on the diagonal. The last time they were all ones, it doesn't need to be all ones. It can be anything on the diagonal. But opposite the diagonal, everything's the same. And that's symmetric. Now, reckon that's always the case? I think it's got to be. If you were to figure these up as Aij, for all the different ones, and then this is AJI for all those, and then you do the thing, you see the off diagonals would almost always have, I think would definitely have to be the same. Now, so it follows that, and I'll write down their conclusion here. It's basically what we just said, that A times A transpose is equal to A times A transpose transposed, okay, which implies symmetric. Okay, because anytime that a matrix and the transpose are the same, it has to be symmetric. That's certainly the case. Now, if you do it the other way, A transpose times A, that also would be symmetric, but it wouldn't be the same matrix. It would be a 2 by 2. Clear? Now, another linear algebra applied into this section. Information retrieval systems, like search engines, they're done with matrices. And just think how many times you've used a matrix in the last, well, before you were even in the class, you were using matrices and didn't even know it. If you did a search on something, you were using a matrix. Not knowing you were using it, but you were. All right. Exercise set 2.2 on page 59. Do any of the odds 1 through 5? Excuse me. Any of the any of the odds 7 through 11. Do number 13.
any of the odds 15 through 19, do 21, 23, 25, 27, any of the odds 29 to 33, and 35. Goodness gracious. I assigned all those before, I'm pretty sure. Okay? So the new ones are 37, either 39 or 41 or both. 43 or 45 or both. Okay. 47 is a true false. So think through that one anyway. My eyes. 49, do that one. 51, it looks really complicated at first, raising a matrix to the 19th power, but do a few and see if you can determine a pattern. Okay? Then 53, kind of the same type thing. You see what you can figure out. Good. Eyes. Do 55. There's a guided proof in 57 you can do if you're not, if you like, and proofs in 59, 61, 63, another guided proof in 65. You can determine if you want to do those or not. I don't know if those answers are in the back or not. I imagine they are. Or also, not just in the back, also at calcchat.com. Okay? I meant to say that earlier. Now, 67 and 69, again, this sort of irritates me. They introduce a new concept. Say they, is he, okay? Introduce a new concept in the problem set. We already talked about symmetric matrices, but here we're talking about skew symmetric. And that definition is that when A transpose is equal to negative A, exactly the opposite way, that's called a skew symmetric. So if this was important, why didn't they mention it in the text? Why did they wait for a problem set? So try to do 67 and or 69. Then 71 and 73 are proofs again, so you decide whether you want to tackle those. 75 is sort of esoteric type problem, almost no numbers in them, okay? And that's the last one. If you want to do it, you can. It's not that difficult, but you determine. All right. Goodness gracious. I think, how are we doing on time? How about let's taking a quick break? I need to go just rinse my eyes out because my they're so dry. All right. 2.3. The inverse of a matrix. Now, a few things we've done. Okay. They're right down next to each other, and I'll get the wrong one. Okay. Transpose of a matrix means you change the columns and rows. It's just sort of a physical thing. You just rearrange things. Inverse of a matrix is a whole different concept. So don't get the two of them confused. I probably shouldn't even bring them up this way, or else you're liable to do that. But they start with this sort of example. What if you had an equation, a linear equation, not matrix, just an equation. AX is equal to B. And I said, how do you solve that equation? Not hard. So don't think I'm trying to trick you here. How would you solve that? Divide both sides of the equation by A.
Now, another way to express that would be, hey, goodness gracious, gray cells are not working. Okay. Is multiply this by 1 over A. Now, that's the same thing, isn't it? Now, here's another way you could express 1 over A. A to the negative 1, okay? That's exactly right, okay? These are all saying the same thing, right? Now, what does it to the negative 1 mean? That's the multiplicative inverse, or the reciprocal, okay? Which is also multiplicative inverse. Now, in pre-calculus algebra, which I assume all of you took at some time in your life, you also came across a concept called the inverse of a function, right? If you had f let's just give one you probably run into more recently. If you had the sine of theta is equal to r, x, or y, whatever you want to call it, let's say y, sine of theta is equal to y, then if you talk about the inverse function, you would say theta is equal to the inverse sine of y, right? Now, we use that same kind of notation, sine to the minus 1. They also say arcsine, A-R-C-S-I-N, but you use that same notation, even though that's not a reciprocal anymore. And none of your inverse functions are reciprocals anymore, but that's what you're using. So this notation is used widely in a lot of ways, and the whole concept of inverses have several different meanings. What we're going to deal now with inverse of a matrix, okay? And by the way, the reason this side works on this last thing is, and they all work, A divided by A is 1, 1 over A times A is 1, and the inverse of A times A is 1, okay? Now, I don't know if you remember when we were doing inverse functions or not. If you did an inverse of an inverse, you're going to wind up with the same thing you started with. It's not 1 anymore, it was x, because you had variables then, not numbers. Okay? Well, guess what? When we do this, and here's the definition. All this is sort of trying to get you to think along the right line. Here's the definition of inverse of a matrix. Number 1. For a matrix to have an inverse, number 1, it's got to be square. A rectangular matrix that's not square will never, ever, ever have an inverse. So, it's got to be square. Now, does that mean all square matrices will have inverses? No. But, in order for it to have an inverse, it's got to be square. So that's one thing. An n by n matrix A is invertible. Now, if that was an A at the last I in that was an A, you would think that would be able to be inverted. And that's exactly what it means. It's just they have an I in there now. If it's invertible, that you could invert it. Now, here's another word for it, okay? non-singular. I kind of dislike the fact that they use these two words meaning the same thing. Invertible, to me, sounds like sort of a positive thing. Non-singular almost sounds like a negative thing. If it's non-invertible, it makes it singular, okay? And I don't like double negatives, but they kind of are. In other contexts, you'll call it non-singular. Okay? It's invertible when there exists and n by n matrix B, notice, has to be the same size. Has to be the same size, and they have to be square, such that, okay, A times B is equal to B times A. Remember back, time out, most of the time this is not true. Most of the time, matrix multiplication is not commutative. We gave several examples earlier of why this is not generally the case. But if these are inverses of each other, if A is an invertible matrix, and you pick the right other matrix B, that you can make that true, and not only is that true, but remember back when we said A inverse times A, and by the way, that's the same as A times A inverse, and what is that both times? When those are just numbers? 1 over A times A, or A times 1 over A, what's that always equal to? 1, okay? What is equivalent to 1 in matrices? What matrix is kind of like the number 1? I think you're thinking right. The identity matrix. And that's exactly the case. The identity matrix. You tell me basically what the identity matrix is? First, what size? Square. Not what size, but what shape. Always square. And what are the characteristics of the identity matrix? Line diagonal, always the ones, and zeros everywhere else. Okay, very good. So that's what makes, okay, so all we've done is now said there exists this other matrix at B, where I, and this I is the n by n identity matrix, so we call it I sub n. The matrix B then, if you found this matrix B that makes that true, then B is called, and you should have it by now, the multiplicative. I sort of never say that, but they say it here. Inverse of A. Okay? Now, if you cannot find, if there is no B, none, whether you can find it or not, if there is no B that will make that true, then we say that A, let me say if, I'll word it the same way they do. I was trying to think of a shorter way to say it. Every way I try to comes out, I think, longer. So let's just say it the way they do. A matrix, okay, that does not have an inverse, and there are plenty of square matrices that don't. Okay, is said to be non-invertible or guess what the other word is? Singular. Okay? again, seems almost redundant. They have two different terms meaning the same things. When one of them's positive, the other's negative, and one of them's negative, the other's positive. Okay. Now, again, they say this right at the end. Non-square matrices. If a matrix is not square, guaranteed it does not have an inverse. Don't even try to find one. Okay? If it is square, it may or may not have an inverse. Okay. All right. And one reason, if it's not square, there's no way that these two can be equal to each other. If this is an m by n, and let's just say this is a n by m, that then you could multiply them together and you'll get a square matrix, m by m. But if you try to do it the other way, and this was n by m, by m by n, then you're going to get an n by n matrix. So, no, they can't be the same. So they got to be square. Absolutely got to be. Okay? But not all square matrices will have an inverse. Okay? Now, wish I had left a little more room, but I didn't, so let me go to a new page and write this one. All right, to erase that. All right. Here's the next theorem. This is a theorem. The other was just a definition. If A is invertible, that's going to be short for invertible, then, if that's true, then the inverse, which it says it's invertible, is unique. In other words, you can't have A here having an inverse B here. And then you can't find some other C that is also an inverse of A. You can't. If you find one inverse of A, if it does have an inverse, that's the only inverse it has. Only one that will work. There can't be another. Okay. Another definition here is the inverse of A, just like we've done before, is called A inverse. Okay? So you don't hang around calling it B's anymore. Call it A inverse. And when you see A inverse, that implies it does exist. It is there. It does have an inverse. Okay. So there's a nice little proof there for that. And I think if you follow that up, you'll see it's got to be true. It kind of says the same thing I said here. AB, if A has an inverse B, in fact, such a nice little proof. If A has an inverse and it's B, that means A times B is what? Earlier definition. This is what identified as its inverse. The reciprocal time itself is 1. So A times its inverse is I. Okay. Now, let's just say that, and if that's true, it's also true that BA is also I. So both of those are true. Okay? Now let's just imagine that there is a second inverse, A times C, that C is not equal to B. Okay? Let's just suppose that there is another one. Okay? Then AC must also be I, and that must also be CA. Okay? Now, what if I were to multiply the outside of this by C? Multiply C here, and C there. Okay? We don't really need the last one. C times A, remember, is also I. Okay? So IC is equal to, and I times C is C. Okay, that's pretty obvious, right? I'm sorry, I did the wrong one. Forget that, sorry. I'm sorry I started this now, because it's pretty simple if you do the right thing. Okay. All right. Let's multiply this by C. And then this will be by C. Okay? And by the way, this will be by C too, but we don't need that one. Okay? Well, CA, remember that the order of multiplying matrices is fine. Doesn't matter. Associative property, that kind of stuff. This times C, this times B, I'm going from here, is equal to C times I, which of course is C. But CA is from up here. I didn't erase them all. I don't need either of those. CA is also equal to I. So this will be I times B. But I times B is B. And here we show that B is equal to C. But we said B is not equal to C. No, it's got to be. There's no way around it. B would have to be equal to C. So there is no second inverse. Okay. Now, because we're using this new nomenclature, the same thing's true down here. A inverse times A is equal to I, and that's also equal to A times A inverse. So all those are I's. Okay. So let's do example 1. That's enough theory. You can almost get crazy going in circles there. Here is A, negative 1, 2, negative 1, 1. Negative 1, 2, negative 1, 1. Here's B. 1, negative 2, 1, negative 1. What it says is to do is show that B is the inverse of A. How could you do that? What's the definition for it being an inverse? A has an inverse matrix B. What's the way to prove that? A times B. Let's do A times B and see what we get. Can you do that? What size will it be? 2 by 2. Can you do it? One entry would be 1. Okay. 1, 2 entry would be 0. The 2, 1 entry would be 0. And the 2, 2 entry would be 1. Guess what that is? That's your I2. Exactly. So, if the product of two matrices is the identity matrix, they have to be inverses of each other. So, yep, we just proved those two were inverses of each other. All right. Want to do it the other way? BA? Let's do it. Let's just rewrite A down here. Okay, and multiply and see what BA is. It's also going to be a 2 by 2. What would that be? 1. 0. 0. 1. Yep. Ding, ding, ding. That's the identity matrix as well. So, yep, those have to be inverses of each other. Okay? So let's see something I said earlier that now I'm bringing it up in the footnote, in the side note. Recall that it's not always true. In fact, most of the time it's not true that AB is equal to BA. Most of the time that is never true. But remember when we were doing it, I said except for special occasions, this is that special occasion. Okay, one of them anyway. All right. Can we do, oh yeah, let's do example 2. Sorry. Now it says find the inverse of A, where A is, too bad it's not the one we just did, it would be easy to find, okay? Find the inverse of A. Well, shucks. What would have to be true? Can A have an inverse? Let's start with there. What's the first requirement for a matrix to have an inverse? Square, and it is. So, it may have one. If it does have an inverse, what size would it have to be? It would have to be exactly the same size. So let's just imagine we have some B here, and let's just name B B11, B12, B21, B22. Okay? And let's say they're inverses of each other. Okay? If that's true, then what must AB be? That I make it I sub 2. You're absolutely right. So, can we do that? Let's see. Let's multiply A times B, and what do you get? It has letters in it. Help me. First row, first column. Multiply these matrices. What would this be? B11, right? Plus 4, B21, okay? Let's get going on it like that. Okay? B11 plus 4, B21, right? Yeah. What does that have to be? 1. Okay? Give me the next one. Let me spread things out a little bit. Okay? I was starting to do that earlier, but I forgot I was going to do that. Plus 4 B21. Okay? Let's do the next one. Second? B12, is that what you said? Okay. B12. I'll put it here. B12 plus 4 B22. What's that got to equal? 0. Give me the next one. Negative B11. Negative 3B21. What's that got to equal? 0. And give me the last. It's B12. Okay. And what's that got to equal? 1. Okay? Now, this seems a little crazy. Let's write that as a matrix, okay? All right to do? I'll have to scrunch it up some. Okay.
Here your columns are going to be the variables B11, B12, you know, like that. And your rows are going to be the equations. So that would be, right, this is a matrix. This is coefficients. 1, 0, 4, yeah, 0, I'm sorry. 1, okay. Got it. Next. 0, 1, 0, 4, 0, negative 1, 0, negative 3, 0, 0, 0, 0, negative 3, 1. Okay? What's the first thing we want to happen? That's a 1. Yay! Already done. Okay? We want zeros below it. It's going to be pretty easy because that's got a 0, that's got a 0. All we have to do is change that one. That's pretty easy. What do we do? Add row 1 to row 3. Okay? So that's the first thing we're going to do. Row 3 plus row 1. Okay? So this will become, don't leave the first row alone. 1, 0, 4, 0, 1. Leave the second alone. 0, 1, 0, 4, 0. New row 3 becomes 0, 0, 1, 0, 1. Okay? And leave row 4 alone. 0 minus 1, 0 minus 3, 1. Okay, I think I'm going to have to get rid of my equations, but you remember what they are, right? Let me just put it. This is B11, B12, B21, and B22. Those are our constants. Just so we'll remember. Okay? Okay. All right. What's the next thing we want to happen? We got a 1 here and 0 below it. Next thing we want to happen is first non-zero entry in row 2 needs to be a 1. Yes, already done. And we need zeros above and below it. Well, we got 0 here and here. That's going to be easy to rectify, isn't it? So what do we do? Say again? Row 4 plus row 2 is going to be the new row 4. All right, so we're leaving row 1 alone. 1, 0, 4, 0, 1. Leaving row 2 alone. 0, 1, 0, 4, 0. Leaving row 3 alone. 0, 0, 1, 0, 1. Actually, we have a solution already for one of them. And the new row 4 is going to be row 4 plus row 2 is 0, 0, 0, 1, 1, right? All right, except for 4 4s, 2 4s that look like zeros, we almost got it, okay? So let's do a quick review. We wanted 1 here, 0 below it, got it. 1 here, 0 above and below it, got it. What's the next thing we want? The first non-zero entry in this row to be a 1, we've got it. And we want zeros above and below it. We've got it immediately above and below. We need that 4 to become a 0. And how do we make that happen? How? Row 1, minus, help me somebody. How do we make that 4 become a 0? Using that leading 1 there. Help me. I'm drowning. No one remembers that, huh? Already turned in the first test. Forgotten that one, right? How do we get that 4 to become a 0? Using this row. Yes. R1 minus 4R3. That's it exactly. Okay? Now, where do I want to put this? I'll put it over here. I'll just scrunch it up really tightly. Okay? Whew. Okay. New row 1 will be what? Second? 1, 0, 0, 0. Second? Second? Okay. Row 1 minus 4 times row 3. -3. You got it. Okay? All right. Now, I'm going to cheat a little bit. Is that okay? We got that 0 where we wanted it. The only thing left is this one. Now, how do we get that? What do we want that 4 to become? A 0. And how do we make that become a 0? Second? Using row 4.
Multiply row 4 by negative.
Exactly. So row 2 minus 4, row 4. Row 2 minus 4, row 4. Okay, so let's go on and do that. And what would that be? Help me. 0 minus 4 times 0 is 0. 1, 0, 0, -4. Okay? And then the other rows we leave alone. 0, 0, 1, 0, 1, and 0, 0, 0, 1, 1. Okay. So what do we have? That first column is the B1. B1, 1 is equal to does it tell us? B1, 1 is equal to -3. B1, 2 is equal to -4. B2, 1 is equal to, and B2, 2 is equal to 1. Okay? So here's what B would be. -3, -4, 1, 1. Okay. Now, that was pretty long and tedious. Easy, but long and tedious, right? Just have to keep up with what's going on. Is there some way we could make this a little bit better? Notice, okay, we started with something. If you looked at where we began, we had a basically a little identity matrix right here. And let's kind of, I don't know if approaching it the way the book does might be helpful. No, they did it the same way we did. That unknown matrix, I called it B, they called it X, is A inverse, which is -3, -4, 1, 1. Okay? Now, this is what I was talking about before. In general, we had, and I erased my equations, I knew I was going to regret those. That first equation, first pair of equations, you had equal to 1, 0 on the end, and the next pair you had a 0, 1. You can tell that here, 1, 0, 0, 1. Okay. At 1, 0, 0, 1, if you put them together, of course, you get an identity matrix. Okay? And this almost seems like a little bit of sleight of hand, but it really isn't. So let me erase this. I hope I won't need to refer to it. If you do, look back at your notes, okay, or the book or somewhere, okay? If you think about this, we were doing a couple of different things. That first set of equations, okay, 1, 4, this was, they called it X11, I called it B11. This is B11, and 4 was plus 4, B21 is equal to 1. See, I regret that I did erase it. And the second was a minus 1, B11, minus 3, B21 is equal to 0. If you think back, that was two of our equations, the two that sort of went together. Remember, I've already erased them all now, but you had these two equal something, and then these two equal something, and then these two equal something, and these two equal something. You took these two that were the same, that was a 1, that's a 0, that's what we got here. Okay? Now, we also had the other two, and they were 0, 1. Okay? Now, if you put those together, oh, we're out of time. Sorry. How did that happen so quickly? Okay? Let me just sort of summarize this. You did the same coefficients, if you remember. The same coefficients you had for these two were the ones you had for these two. The same coefficients these two were for that two. This gave you 1, 0, that gave you a 1, 0, that gave you a 0, 1. If you put that together like this, we had A11, A12, A21, A22, and then the first was a 1, 0, and the next was a 0, 1. And then you did row reduction, you'd have gotten the same thing. And what you wound up with was your B11, B21, B12, B12, B21, and B22. Lo and behold, that's what you wound up with. And when you did the row reduction, you wound up with a 1, 0, 0, 1. And then you had, I'm sorry, these were already here, okay? And what you wound up here is your B11, B12, B21, and B22, okay? When you did that. And it just was rather bizarre. You start with A times I, do row reduction on it until you get I, and what you have at the end is the IA inverse. That's the key. That's what we were doing. We will pick up from there and use that to do finding inverse of a matrix by Gauss-Jordan elimination, which is basically what we just did. I'll make sure I don't have more arrows on this page. Homework exercises here. I think you can do any of the odds 1 through 5, and these are calcchat.com as well as the back of the book, and we'll hold off and do the rest of those later. So do any of the odds 1 through 5. Right, good deal. Sorry, ran out of time. Went fast. Good deal. Thank you. And we'll catch you. Have a good weekend. By the way, and we'll see you next year.